intensity. It's supposed to be the last two lines.
Last 2 lines.
Yeah. So this is the response. The temperature on the surface should respond this way, if we assume classical heat transfer model. And this way you can rewrite it in a more simplified form into that way.
So that's what I want to hear. You said simplified.
Yeah.
It's not physics. It's approximation.
Just from here.
Here's the physics I know.
Yeah.
But the next slide is I have seen that one get surprised.
This one?
No, next. Okay, this one. You got this sine omega plus delta. This one is pretty surprising to me. It's linear time invariant system.
So you're saying the omega in a damped oscillation system, the omega changes. I know. Yeah. In this system, can you go back one slide?
It's not obvious to me. Yeah. Maybe this
Yeah, it's not obvious actually.
Yeah. All right. So.
Yeah. We can talk a little more. Yeah.
Okay.
So let's move on to.
Thank you, Zalong. Yeah. So can you finish in 5 minutes?
I think so.
Okay.
What's your laser source?
Just a pump laser.
It's a very, very interesting system.
Okay, all right. My name is George Song. I'm a PhD student in mechanical engineering.
Stand on the side. Yeah.
All right. And to advance my wider.
Okay.
So what I'm doing, my research is all about nano flow and macro flow. And we're trying to develop theoretical models and trying to verify these experiments. So here I want to, I think today I'm going to see the potential application of fractional calculus in this field. So I'm going to focus on the mathematic features of nano and macro flow. Here we go. The nano and macro flow, what is that? We can barely get the concept from the name. Nano and macro actually is the flow through a channel or a capillary or whatever. But the size is just at nanometers or micrometers, very small. But if we get a little more insight, then we can see. I would say, if there's no EDL there, if we don't consider EDL, then there's no nanoflow or macroflow. So what is EDL? Actually, EDL is pretty common. If we put water on this table, we'll see EDL at the interface. At the interface of water and
However, EDL to me is capacitor. Is that right?
No, it's electrical double layer.
Right. All right. Electrical double layer.
It's similar. Yeah, it has a capacitor in there.
And then what in EDL is in EDL there is ions distribution. It's non-uniform ion distribution, and there's also electric field in the EDL. So, well, actually the EDL is pretty common, as I said, to put order on the table. But we don't consider EDL. Don't consider the attribution of EDL to the flow. In normal case, it's because the thickness of EDL is pretty small. It's very small. It's about typical values of the EDL thickness varies from 10 nanometer to 1 micron. It's 10 microns. So when the size of the channel is pretty small, it's at the similar magnitude of the EDL thickness, then the contribution of EDL to the flow is pretty important. Well, here is the Gaussian equations. This is the first three is the traditional equations, except the terms, the last two terms there. That two terms account for the attribution of EDL. This part is we call it space charge density, and this part is called the effective field. So because we have electric field and we also have ion distribution, then we use Gauss law to combine them to describe these two
accepting your momentum equation, you have two macroscopic thermodynamic properties. One is the pressure,
Right.
and the other is the kinematic viscosity,
Right.
that are only defined for macroscopic systems. And you want to apply this to a microscopic system.
Well, actually, these two also, it's not that small. I mean, the continuum theory is still available at this size. But for 1 micron, probably, I guess
That's pushing.
100 molecules, 100 molecules in 1 nanometer. So we can see the 1 micron, there will be 10,110 molecules there. So the continuity equation is still available.
But there's also assumptions about homogeneity and isotropy that are implicit in these equations. And when you're down at that small scale, what becomes important is anisotropy and heterogeneity and non-homogeneous distribution of particles. All that becomes important. What kind of modifications in the constitutive equations are implied by that? They become very important when you
Yeah,
go to the
that's true.
microscope.
I have never studied about. But thank you.
Okay, when you start to think about it, you will meet fractional calculus. That's why Professor West is trying to.
This is also the just totally a macroscopic treatment.
Okay.
Yeah.
Yeah, but I'm just voicing caution.
Yeah.
I heard a few times about the portion from you.
So these gamma equations are well known and well all accepted. So what I'm doing right now is trying to check the physical meanings. Actually, we need other constraints like boundary conditions. For this one is on the boundary conditions at the surface. And we also probably need these conditions to solve the whole the equation systems. So after this part, what we're doing now, we're trying to apply this one or that one kind of thing, and then to get some solutions. And here is we see the Boson-Boltzmann equations. Actually, that's Boson equation. This part. And this part is space density, space charge density. But here we resolved from spatial conservation equation for 1D. So we have already solved the 1D equations. Boltzmann equations. Normal case, usually we try to divide Hooker approximation to linearize this one, the nonlinear term right here. Or in some cases it can be simplified to 6 Poisson equations, this. But here, our group trying to introduce this one by ignore the effect of co-ions on the EDL, because for overlap the EDL, this works. Overlap the EDL only. Then this is for this is a mathematical model for 1D channel flow. This whole equations right here we are using to resolve the 4 Gaussian equations. We already have some. This one we have solved, so we compared this because we use these equations. This is analytical exact analytical solutions we can get from this one, and this one will be,